Hello and welcome to my channel and to this video in which I'm going to talk about Milky Way time-lapses and skyscaping, landscape photography on the dark side of Earth. I'm Michael Stolz, and this was a talk that I gave on the 17th of May 2022 at the Astronomy Club in Aalen. I'm going to give a short introduction to landscapes and skyscapes. Then I'm going to talk about the basics, theory and practice. And then I'm going to give some examples. And throughout the talk, there are going to be many examples which show what I'm talking about. Yeah, landscape is basically landscape pictures that you do of the day or also on the night, but the focus is on the ground. Having some nice mountains and clouds and rivers and so on. And skyscaping is basically the same thing, but the focus, the emphasis is not on the ground, but more on the sky and on the stars. And these are some examples of skyscapes. Up here you have a panorama. It's actually a 360-degree panorama of the sky above La Palma and also the silhouette of the landscape beneath it. And you can actually also turn this panorama and look around as if you were standing there. This is one example. And then here another example. This is a time lapse of the night sky above the town of Oberkochen. You see here the constellation of Orion and the constellation of Taurus, and here some part of the winter Milky Way. You have down here the illuminated cityscape of Oberkochen, a suburb of Oberkochen. Up here, the Heide, and you see the traffic as it moves, and you see the stars as they move, and the clouds. Another example is skyscape and time-lapse of the Milky Way above the Caldera de Taburiente. This is on La Palma. You see the clouds as they move down in the caldera, and also as they go over the Cumbre Nueva. You see the clouds illuminated from below, from Los Llanos and Tazacote. And of course, up here you see the central part of the Milky Way as it moves across the sky. This is probably around 3 or 4 hours in real time. Another example here, again, La Palma. Now the Caldera de Taburiente down here is filled with clouds. You see Pico Behenato sticking out its head just above the clouds. Here the trick is, this is a time-lapse that covers the night and day also. Here some little mishap happened. Actually, the tripod moved during the when I made the time lapse. But anyway, it's just an example for what skyscaping and time lapses of the night sky can do. Another example, well, that's basically the same thing. Oberkochen, the stars. Here you see Andromeda, you see the Pleiades and the Milky Way. And another 360-degree panorama. That's a place at Wental, close to Oberkochen. And here you can also look around in all directions as if you were standing here. Yes, you see Orion and the winter Milky Way. And on the ground you see some remainders of snow and some simple setup that I put there for doing some other exposures for something else. And the goal is to make it possible for anyone to experience the beauty of the night sky. Now I'm going to talk a little bit about the basics of how to make such panoramas, skyscapes, and time lapses. Basic things to note here, especially in comparison to classical astrophotography. You often do only one single exposure. You do no stacking typically, or often. You can, but you don't have to. So that means you have to optimize your single exposures as best as possible. Often you're not doing any tracking, but of course you can. That means, the stars, well, if you do tracking, then the stars are going to be sharp and the ground is going to be blurry. Or if you don't do any tracking, then you have a limit on how long you can expose the stars in one single exposure. And typically you are pressed for time, because for time lapses you have intervals. Each single exposure is going to take a certain time, and after a certain interval comes the next exposure. And if you want to do any changes, any adjustments, you only have a certain amount of time to do those. And for panoramas and landscapes with the sky, you have to always consider that, of course, the sky is turning, it's continuing to turn. And if you make, for example, a 360-degree panorama, then the sky has turned for, let's say, 5 minutes, but of course the ground hasn't. And so you have to make that time as short as possible. Okay. Now, basic parameters that you have to consider for making those pictures is the focal length, the exposure time, the aperture, and ISO. I'm also going to talk about what is Holy Grail time-lapse and what is the appropriate equipment for taking such pictures. Well, the focal length depends on what you want to shoot. Different focal lengths have different field of views. Our human eyes, for example, have a field of view of about 140 degrees by 80 degrees, and a 14 millimeter photo lens will have a field of view of 100 by 80 degrees, and for example a 100 millimeter lens has 20 degrees by 14 degrees. And you just have to think about what picture you want to take, what is the subject that you want to capture. For example, if you want to capture the Milky Way as it is spanning from horizon to horizon, that means you have 180 degrees by, let's say, 20 degrees, which is about how broad the Milky Way is, then you can consider what kind of equipment you use or which focal length you use. And you could do this, for example, with 3 or 4 exposures with a 16 millimeter lens, or with like 6 or 8 exposures of a 50 millimeter lens, or you could do this picture with a fisheye lens, which of course sees the whole sky. Or if you just want to take a picture of the central region of the Milky Way, which has 80 degrees by 30 degrees, then probably yeah, a 14 millimeter lens would be good. If you would just want to take a picture of a constellation, let's say Orion, which has a size of about 25 degrees by 15 degrees, then a 50 millimeter lens would be nice. Or if you want to just take a picture of Barnard's Loop, which is a part of Orion, then you might do well with a 100 millimeter lens. And if you want to take pictures of small nebula, for example around Rho Ophiuchi or North American Nebula, those are much smaller. I mean, the largest of them, no, not the largest, but typically the larger ones are like 5 by 5 degrees. And for those, 100 millimeter focal length is already rather large, but you could see still those objects in there. A 200 or 400 millimeter lens would be better, probably. Yeah, altogether, landscapes together with the Milky Way or similar, you should choose a 20 millimeter focal length or shorter, that means wider. And if you want to take pictures of details in constellations or single nebula, then longer focal lengths, like 35 millimeters or longer, would be better. And you can use Stellarium, for example, or other planetarium programs. They can help you to see in advance what the field of view is on the sky. Here, for example, Stellarium shows you what a 14 millimeter lens on a full frame camera would show on the sky here. This is the red square here, and it has a tool where you can enter several different sensors and different telescopes or lenses, and you can switch between different equipment basically on the program. And here you can see, if you want to expose the nice central part of the Milky Way with a little bit of that part also and a little bit of the ground, then here obviously the 14 millimeter lens would be a nice choice. And this down here shows an example. This was shot with a 14 millimeter lens. This is a day to night time lapse, a so-called Holy Grail time lapse. Actually, not a very good one, but you can see on the left side the summer part of the Milky Way rising now. And just before that happened, and I will keep the time lapse running so that you can see it again, you will see then also the winter Milky Way setting. Here the sun is still up, and then night comes, and now on the right side you have the winter Milky Way setting, and underneath you have a landscape where you have clouds slushing around, and you have in the background the Tenerife and land, and down here, of course, La Palma. Yeah. Or if you want to choose a 16 millimeter lens, you just enter it in the Stellarium, and it shows you now a smaller frame here. And this is also an example here. This is in Germany at Heubach, not very impressive, but I think you get the idea. You can choose in advance which kind of focal length would be the right choice for what I want to do. This is now an example for a 50mm lens here around Cygnus, here with the North American nebula, and I actually have almost that frame here in reality. So you see here North American nebula. This is a little time lapse. I actually did many single exposures to do some stacking, but of course you can also use those single exposures as a time lapse, and you can see those many satellites as they cross through that region. Yeah, 50mm lens would also show on the center of the Milky Way a little bit more detail. This is a dark horse with Rho Ophiuchi and a lagoon nebula, and so forth. Or, I mentioned before, 50mm would be great to show a complete constellation. In this case, it is the constellation of Orion. You see here Betelgeuse. It was back then pretty orange. And you see Barnard's Loop here. And the Orion Nebula down here, very tiny. You would see the Horsehead Nebula. And you see some fog moving across the image. And here the Milky Way. And here, unfortunately, trains of satellites, probably Starlink in this case here. But you can see that you get a nice view with a 50mm lens of Orion. Okay, now let's move on to exposure time. With exposure time, you have to always think about the fact that Earth is rotating, and that means, from our point of view, the sky is rotating, and so the stars are moving, and they are in fact moving up to 15 arc seconds per second when you don't correct for that motion in your telescope or in your camera. And for that, to think about that, is we have the so-called 400 rule. And the 400 rule helps you to find the correct exposure time so that you collect enough light per pixel without creating star trails. Because if you expose too long, then this picture of the star will move on and on due to Earth's rotation to the next pixel, and then on and create a little trail here. And that causes, of course, the collected light not to be collected on one pixel, but spread out on several different pixels, and also creating lines instead of points, which we don't want to have. And if you use the 400 rule, you are exposing short enough to prevent this from happening. And the rule says basically the maximum exposure time is 400 divided by the focal length in seconds. This rule is only really a rule of thumb. There are more precise rules, for example, the NPF rule, which is used in photopills, and there you also have to consider the pixel size and where on the sky your object is, because if you take pictures close to the celestial North Pole, for example, Earth's rotation will not be such a big issue, but if you take pictures close to the celestial equator, then Earth's rotation is an issue. Okay, I actually don't really use the 400 rule. Over time, I decided on these times here, which are shown in this table here. When I use my 14mm lens, I only expose a maximum of 25 seconds. The 400 rule would say almost 30 seconds. If I have a 16mm lens, I only expose maximum 20 seconds, and so forth. If I have a 50mm lens and I don't have a tracking device, then I would only be able to expose a maximum of 5 seconds without having trails. And these times here are for my cameras, which are two Canon 6Ds and one Canon 5D Mark IV, and they are 20 megapixels or 30 megapixel full frame cameras. Of course, if you have a tracker, then you don't have those time limits. Then you can expose for much longer times. I myself did exposures of up to 300 seconds for focal lengths of up to 200 millimeters. Of course, then only the stars will be sharp and the landscape will be blurred. Okay, now to the next thing to consider, and that is the aperture. The aperture basically is how large the opening is in the photo lens of your camera. And I, for example, have a 20mm lens which has written on it f1.4, and that 1.4 is the largest opening it can have. And small numbers basically mean large openings. And down here, that graph shows on the y-axis basically a measure of how optimal this is, and on the x-axis I have here the f number. I start on the left here with f31. This is the smallest possible opening for that lens, and that would mean I would have really almost no light coming through and almost no resolving power with that lens. And if I open the aperture more and more, I get more and more light, so it's getting better and better and better. At f11, that lens would have optimal resolution, but at f11 the hole in the lens is still very small and I have almost no light coming through, so I have very little light. That's not a good setting here for photographing the stars. So if I open the aperture more, then I see at a certain point I reach an optimum, and then it goes down again. And why does it go down? I continue to have more and more light if I open the aperture more and more, but I start to have other problems then. I start having lots of aberrations, that means imaging errors, and in the end I have bright images but very bad images. So in the end we have somewhere in between here an optimum for the aperture. I can do the same thing, of course, for exposure time. There it's rather obvious. If you expose very short, it's not optimal. You have almost no light. And then you increase the exposure time, you get more and more light. But at a certain time, then you don't get anything more out of exposing longer. And that is because then you start to have little star trails on your sensor, and the images of the stars are not getting brighter anymore, but they are getting smeared on star trails. So this optimum goes down again, and this is due to the 400 rule. And so here for that lens, there would be an optimum around somewhere around 20 seconds or so. Just a quick word about depth of field. I mean, anybody who does photography is aware that taking pictures with very, very open lenses has the problem that you have a small depth of field. And that is not a problem here in astrophotography, or not a large problem. Yes, you have a depth of field, you have basically a kilometer around you not in focus, but the whole rest of the universe is in focus, so everything is fine basically. What you have, and what is more important, is that you have more aberrations if you have larger apertures. That means smaller f numbers. Now we come to setting the correct ISO. And that basically means utilizing the analog to digital converter correctly in your camera. And I'm using here again my two types of cameras that I use, the 6D and the 5D Mark IV. And yeah, those numbers here fit well for f1.8. So here again, on the y-axis is how optimal I see this certain situation, and on the x-axis I have the ISO. And here, same game again. It should be actually a linear curve here, but it doesn't really matter here. At ISO 400, you have almost no information in the picture. It's too dark. And then you increase your ISO and you get more and more light. And then you have an optimum, but then it goes down again. And that I'm going to explain in a moment. And basically what's happening here then is if you increase beyond that point here, you don't get more information into the image. All you're doing is you're amplifying your missing information, and you're increasing the noise in the image. So if you have low ISO and you look at the so-called histogram, you would see if you have an ISO 400 that your histogram is somewhere here on the left side of the histogram of the graph here. All the information of the picture is somewhere cramped here on the left side and happens within basically just 500 brightness levels. And if you increase the ISO, then this histogram is going to be smeared or distributed more and more across the whole graph. And here, for example, at 800, then your whole image happens within 1000 brightness levels. And here, over here, your image has about 8000 brightness levels. And the more brightness levels you have, the more you can do editing in the end. The more details you can get out of the picture. And how does this histogram work here? How is it? How do you interpret it? Basically, if you look at such a curve here, you have here on this side how many pixels have black values, and on the right side you have how many pixels have the full white values. And here, for such picture of the Milky Way, for example, it would be here, this here would be the black background, and then this curve, this part of the curve, would be the structure in the image. So for example, the Milky Way and the clouds, and this little tail here could be the overexposed single stars. And if you manage to have your image coming up like this in the histogram, then you have the maximum amount of brightness levels available for a 14-bit camera like my Canon 6D and the 5D. This would mean you would have around 16,000 brightness levels that you can use to show all the details in editing. Okay, so I'm trying to explain here now how you can interpret the ISO. And you have here on the left side different bright stars. Up here you have a bright star, and it sends to your camera a lot of photons, and those photons create on the pixels on which they land, they create here electrons, or they free electrons, and the amount of electrons you have on the pixel depends on how many photons land on that pixel over the exposure time. So once you have exposed the image, then this contents of the pixel is sent to the analog to digital converter, and you basically can think of it as a scale, and it measures how much charge is in this pixel and converts this amount of charge into a number between 0 and 16,383. So if you have a lot of electrons in here, then it's going to be a large number, close to 16,000. If you have a dimmer star on that pixel, you have fewer electrons on the pixel, and therefore a smaller number. And if you have a very dim star, you have much fewer electrons, and therefore also a smaller number here. So now, if you change the ISO, basically you change how fine or coarse your balance is. If you have a lower ISO, then the balance is not as sensitive to the amount of electrons you have in the pixel, and you get, for this amount of electrons, you get a low number. Of course, you have to consider that if I have now here 2 or 3 electrons more, it probably doesn't make a difference here, because here it can only go in steps of 1. And if the balance is so coarse that it's so insensitive, then a difference of a few photons wouldn't make a difference here. If you have a fine balance, on the other hand, the same amount of electrons in the pixel creates a very large number here. In this case, a large number, 6,400. There's 6,400 steps from 0 to up to this here. And if we have here just 1,000 electrons in here, then one more electron would actually show up here as 6 figures higher. So higher ISO would be better, but not always, because it's not just a pretty world here, but you also have other influences on the image, and that is, for example, readout noise and thermal noise and so on. And I showed them here as a little bird which ticks on the balance here, and the coarse balance will not be impressed that much by the bird, but the fine balance will show changing values every time this bird is knocking on the scale. So with higher ISO, you will have higher noise in your images. And at a certain point, if you just use a higher ISO, you're not getting more information, because if you just have 1000 electrons in here in that pixel, and you have and you magnify this to 6000, basically there is not much more information. Every more electron goes 6 steps up, so you could have used here just an ISO of around 6400, and then each single electron would have made 1 step up here. That would have been fine enough, and 32,000 would not give more information than 64,000. Sorry, yeah, 6,400. Okay, so altogether you have a given, and that is, what do I want to photograph? And with that you choose a photo lens which has the correct field of view, and then you start maximizing the exposure time using the 400 rule, and so that the stars should be dots and not trails. And then you choose an aperture, and an aperture that is as maximal as it could be without creating imaging errors. So if you have a f1.4 lens, typically it's not wise to use 1.4, but to use 1.8 or 2.0 or 2.2 or something, just to reduce the imaging errors. And then you maximize the ISO so that you utilize your 14-bit depth of the camera well, without creating noise and without creating empty amplification. And I'm showing an example here which shows all of those factors. Here you have, again, the center of the Milky Way. Down here you have clouds above Caldera de Taburiente, and now this was shot with 16 millimeters at f2.8 with 20 seconds exposure time and an ISO of 6400 with a 6D before I had it astro modified. And here you see the histogram, and that doesn't look too bad. You have here, this part here is probably most of this dark area, and then in here is all of this information. So this here, you want to be spread as wide as possibly across your histogram to have all those brightness levels. And since I used here f2.8 on a lens that only goes up to 2.8, I have here imaging errors, and I have here in this corner, for example, and in every corner, I have pretty rancid coma, yeah, and these coma pictures would be minimized if I had chosen a smaller aperture. And down here you see that I have quite a lot of noise in the cloud, and this is completely normal because this is a single exposure, and you have always noise, but this noise would become higher if you would do shorter exposures. For example, if I would have only exposed for 10 seconds and brightened the image then later on in Lightroom, then I would have had the same appearance of the picture altogether, but I would have more noise here. And I can also show you the effect of too few photons here in the corner. I have this weird pattern here, and that comes about when you have very, very few photons coming in and creating this strange effect. And this comes because Lightroom here did a correction for the lens and brightened the corners because of the effect of the lens here, and then it doesn't have anything to work with, so it creates this noise pattern here. And what do we see in this picture? Yeah, well, the Milky Way. You see the mountain of Pico Pericoyo, which is about 17 kilometers away from my point here, and have the island of La Gomera, and then Tenerife here on the horizon. Here Pico Bejenato just sticks out of the clouds, and I have here an idiot who thinks he has a moment here with nature, but of course everybody else who was up here at the same moment also had to have the same moment that he had, because he was shining his bright light on the cloud cover and was probably surprised that he can create a light spot on the cloud cover. So I would ask you not to be like this person here, because this is an area of around 10 kilometers, and everybody else here in 10-kilometer distance had to have this change in the scene because this person did this here. Okay, and now I mentioned several times the word Holy Grail. Holy Grail time lapses are time lapses where you adjust the exposure time and the ISO during shooting during dusk or dawn. So during dusk or dawn, when you start, for example, at daytime and you go into the night, then you have orders of magnitude of brightness that you're losing from daylight to night. And the camera, as you saw, has only 16,000 brightness levels and would not be able to cover this change in brightness. So you have to constantly change the exposure time and then later on the ISO to always have a correct exposure, to always have an optimal exposure while you're shooting the time lapse. And I can show you how this would look if I didn't do anything more to that time lapse. So here I have nighttime. This was before editing, and now it's getting bright, and you see you have this flickering. This is I constantly shorten the exposure time as it's getting brighter and brighter and brighter, and then you have this flickering, which you don't want to have. And to remove this flickering, you can use programs, and for example, a very, very nice program is LR Timelapse, and it analyzes your single exposures of your timelapse and notices that you change the exposure time and corrects then the brightness of the image correspondingly. And when I'm doing this then with LR Timelapse to this timelapse here, I get then this. You don't see any flickering anymore, and it's a almost smooth time lapse. This is actually a good example also for a different mistake that I did here, and that is in this example I didn't just change the exposure time, but I also touched the aperture. And this is something you should not do, because the human eye is very, very sensitive to the brightness distribution in images, and that changes when you change the aperture. So you see here some dark spot suddenly coming here and vanishing again, and that comes because I changed the aperture. And when I noticed that, I was on vacation and I noticed this, then 2 days later I repeated basically the same time lapse again without using aperture, and then this is how it would look without changing the aperture. I don't know why it's a little bit flickery at the beginning, but you see here you see here very smooth brightness changes. And I don't know what the rendering problem is at the beginning here of the time lapse. Okay. And with Holy Grail time lapses, I said you have to correct constantly your exposure time or the ISO, and you have to do that yourself because the automatic exposure of the camera is insufficient in that case. As soon as it gets really dark, the camera cannot really measure good enough the exposure time here. You can use other methods. You can use, for example, an app on your cellular phone. QDSLR dashboard I used, and this would download a preview image from your camera and looks at the brightness levels and then adjusts automatically always the brightness, but I'm actually doing this manually. And in any case, when you're shooting a time lapse and you're doing changes to the settings during the time lapse, you have to plan for a minimum dead time that you need, or that the app needs to do those changes. So let's say here I can do changes within 5 seconds on the camera. Then if I have an interval between pictures of 20 seconds, then my longest exposure time would be 15 seconds. Because then I need the time to change the exposure time or the ISO again. So, and you have to plan for that in advance. So in the end, that means basically you have to choose a long enough interval so that you can have always enough time for making the adjustments. Another thing is choosing the appropriate equipment, and that is, for example, here with I'm just comparing here cell phones with full frame cameras, because there are many people around who claim that you can do everything with an iPhone or with a Samsung or whatever that you can do with a DSLR or with a mirrorless camera, and that is not so. And that is not so because of physics. If you have a cell phone, it has a very small, comparably sensor. In this case, my old Note 9 had a sensor of 5.8 millimeters by 4.3 millimeters, and the pixel size on that phone was 1.4 by 1.4 micrometers. If I compare that to what I have in a Canon 6D, which is a rather old camera, yeah. And here I have a 36 millimeter by 24 millimeter frame, and this is drawn, the comparison is to size here. And here I would have a pixel size of 6.7 by 6.7 micrometers. That means those pixels are more than 20 times the size here, or about 20 times the size. And so those pixels can collect many, many more electrons, not electrons, photons, and convert them to electrons. And so cell phones will always be worse than DSLRs or mirrorless cameras for astrophotography. Besides the small sensors, they have only limited manual modes, whereas real cameras have full manual modes. The small pixels I just talked about, yeah, and connected to those small pixels, you have high noise in those cell phones, and that's why they only let you choose up to a certain ISO here, and they only let you do shorter exposure times. Yeah, and on a mirrorless or on a DSLR, you also have noise, but it is limited in comparison to cell phones. And last but not least, with cell phones, you don't have interchangeable lenses. Whereas here, with real cameras, you can change the lens and you can choose an appropriate lens for what you want to photograph. So my advice would be, use rather a 5-year-old DSLR camera than a brand new cell phone when you want to do astrophotography. And this was an example taken with my Note 9 cell phone of the center of the Milky Way. It's an effective focal length of 4 no, not effective, it's a physical focal length of 4 millimeter at f1.5, 10 seconds exposure, and the maximum ISO of 800. And you can see the Milky Way, which is really nice. You can see the dark horse, you can see all those details more or less. But compared what you can take with the Canon 6D with a 14mm lens, f2.4 and 20 seconds at ISO 6400. And this is a picture which I didn't take to just be especially perfect. This is just a frame, a single exposure of one of my time lapses. Yeah. Okay, now I'm going to continue with some examples, and this is to show you that you can also shoot in not so perfect areas the Milky Way. This is on Volkmarsberg. This is a mountain close to Oberkochen, my hometown, and you have the winter Milky Way. Actually, this is up here, Cygnus. The Milky Way turning around while some people down here are sitting around. Or here, another Milky Way above La Palma with the clouds moving across Cumbre Nueva, and here in the Caldera de Taburiente. This is actually one of my favorite time lapses. I mean, it's also one of my oldest. You have quite a busy landscape down here with lots of clouds and changing. And up here, the Milky Way. You can also see, by the way, here everywhere satellites. And if you look closely enough, you can see here geosynchronous and geostationary satellites everywhere here. You can actually, if you know exactly the time at which this was taken, you can actually identify which satellites those are up here. Another example here, and by the way, every time I have here this cloud with this flash, there's going to be a little dust trail from a meteor also in this time lapse. So here, this is Tenerife. The clouds here are clouds just above the ocean, the Atlantic. And the Milky Way is rising above Tenerife. And somewhere up here, I think, was the, yes, up here, was the dust cloud from the meteor. Up here. Now. Yeah, here the same thing. I don't remember where the meteor was. Here. Yeah. Ah, here. Here was the meteor. Here, it's coming. Yeah, there it was. Okay, you can also make panoramas, of course, of the night sky, here in this case with the silhouette of the ground. And you have the arc of the Milky Way here, up here. This is on Pico de la Cruz on La Palma. You can see the Dark Horse, Rho Ophiuchi. Here you have the Lagoon Nebula. Here the False Comet Nebula. Up here you have North America Nebula. Yeah, and here the dark dust clouds of the Milky Way. And here more time lapses. And basically the main thing is always the landscape below. Here is where most of the action is, because the Milky Way is not really that much different every time. You can also make some changes here. This is not a stationary camera, but I put my camera on a slider and also changed the direction in which the camera looks at during the time lapse, and this makes for a totally different experience here. Yeah, and here, up here, I can show you a detailed horizon to horizon panorama of the Milky Way. This was shot with 50mm focal length and with a Canon 6D after it was astro modified, so it is more sensitive to the red light here. You can see here Heart and Soul nebulas and the North American nebula, and yeah, here Eagle Nebula and Lagoon Nebula, and the Dark Horse with Rho Ophiuchi, yeah, from horizon to horizon. You can also just use a fish eye lens and you will have the complete sky. But I actually don't like this that much, because I think that the landscape underneath the sky is the actual star of the scene. And here you just have the Milky Way as it passes across the sky. This is also made with an older camera, with the Canon 70D, with an APS-C sensor, a smaller sensor, and so therefore I had more noise and less details in this image. Yeah, you can also use a tracker so that the camera always looks at the same point in the sky. The tracker corrects for Earth's rotation, so it looks now here in this time-lapse as if the sky is stationary and the Earth rotates around here. This is actually how it actually happens, but to us it's a very unfamiliar point of view. And you can see here the Andromeda galaxy. You can see somewhere I saw, did I see the Pleiades here? Yes, down here the Pleiades. Up here you have again Cygnus with the North American Nebula, and somewhere here is Heart and Soul, but this is not with a astro-modified camera, so I don't see them very well in this image. And you can also photograph special situations or special occasions in the sky. In this instance here, I noticed that you can see the zodiacal light very well on La Palma. And the zodiacal light is this cone of light here. This is scattered light here in the plane of our solar system. And you can very easily make pictures of it on La Palma. You can see here the winter side of the Milky Way. You can see here Orion, the constellation of Orion, with Betelgeuse, the Belt stars, and Orion Nebula, and Barnard's Loop. So the fact that I have here the Barnard's Loop here means that I shot this here with an astro-modified camera. And down here, of course, then the clouds above the Atlantic. Or here in 2022, there was a situation where you had Saturn, Mars, Neptune, Venus, and Jupiter. Jupiter is this one here. Almost like in a string here, rising, and then also the moon lit 90%. And in addition, you have here the display of those crazy clouds rushing over the Atlantic and Tenerife here at sunrise. And I showed you several times that you can also catch meteors with dust trails. This is not such a rare occasion. I noticed that people on Instagram always are very, very happy and proud and whatever when they catch something like that. But in fact, if you shoot time lapses, you will get many, many, many such instances. And I also showed you the satellites here a little bit more magnified. Here you have these geostationary satellites and then these slow moving satellites which are geosynchronous satellites. Yeah, same thing. Everywhere here. Like pearls on a string here. And then you also have outrageous satellites, stupid satellites. I think I showed you this example before. Yeah, these trains of satellites here, and I'm not looking forward to the time when we have 20,000, 40,000 little satellites up in the sky so that everybody can watch YouTube videos somewhere in the mountains, because then you cannot look at the sky anymore in this way here. Yeah, and of course you can also, when you're lucky, you have special occasions like Comet Neowise in 2020. This was just before sunrise. And this is also a Holy Grail time lapse. I had to constantly correct for the exposure time and ISO. And here, Comet Neowise a little bit more in detail. This is with a 100mm taken. You can clearly see the ion trail and the dust trail very well separated, and you can also watch how the comet moves across the star background. And here another 360-degree panorama of Pico de la Cruz with the Milky Way. You can look around in all directions. In this case, I didn't shoot many pictures of the ground and just of the sky. Yeah. I like those very much because you get a feeling how it looked when you were actually standing there. Of course, you don't see the night sky as bright as here, but you sort of have the feeling when you're standing there as what you have when you look at this 360-degree panorama. Okay, and that concludes the talk.